Hello, I'm Peter Hollemans, and this is a presentation for the PolarWatch Sea Ice training course. I'd like to talk about some of the ways that performing calculations on data can be affected by the choice of map projection. And so about me, I have a background in physics and computer science, and I work with Michael Sirocco at CoastWatch Central Operations. One of my main activities is to maintain a package of software called the CoastWatch Utilities, and that helps users work with CoastWatch data and files. I won't be showing that software specifically in my presentation, but I did use it to prepare the figures and perform calculations, and I'll show a few code snippets that you can use with that software. So I'll show examples of how the map projection affects data analysis, the statistics and the histogram of the data, the size of pixels and measurements, like sea ice extents, and how line surveys are affected. I'm going to use a cylindrical projection and compare it to a planar projection. So the geographic projection you see on the left, sometimes called equirectangular or a plaque carré, is based on a cylinder surrounding the Earth, as you can see, and it keeps lines of latitude and longitude equally spaced and straight at the expense of distorting the areas closer to the poles. So now the polar stereographic projection on the right is planar because map features are projected onto a plane that's either tangent to the Earth or cuts it at some location. And in this case, it's centered on the North Pole, and it shows latitude lines as circles and longitude lines as converging at the pole. And the areas close to the poles show only minimal distortion. So for example, look at Greenland. That's the true shape of it when you would look at a globe of the Earth. Let's take a closer look at the geographic map projection. On the top left is a diagram of the Earth shown as if you're holding a globe in front of you in your hands. You can see how a vertical sliver of area on the globe, say near Greenland, translates into a square area on the geographic map projection. But a roughly square area further from the pole, like the one highlighted over Spain, also translates into a square area on the geographic projection. And so what that means is that areas of equal size on the geographic map don't equate to the same physical area on the Earth. And when I say physical area, I mean the number of square kilometers. So in fact, pixels on a geographic map projection at about 60 degrees north or south are about half the physical area on the Earth as pixels at the equator. And you can see that in the table and the graph. The table shows the ratio of pixel area at various latitudes to pixel area at the equator. It's 1:1 at the equator and half that, or 0.5:1 at, say, 60 degrees latitude. At 85 degrees latitude, it's even worse. The pixel area is over 10 times smaller than at the equator. And you can see the relationship between pixel area and latitude on the graph at the right. It's showing visually the same thing as the table. So now let's take a look at the same thing, but for a polar stereographic projection. Here's a similar diagram and table, but for a polar stereographic map projection. So again, on the top left is a diagram of the Earth, as if you're holding a globe. You can see how a square area on the globe on the south end of Greenland translates to a square area on the polar stereographic map projection. And a square area further south, say over the Red Sea, also translates to a square area on the polar stereographic projection. That's in contrast with the geographic map, where pixels became smaller and thinner in physical area towards the pole. The two projections distort map areas in different ways. So you'll notice that although the coastlines on this one have the proper shapes, the polar stereographic map makes areas look progressively larger as you go south away from the pole. And in fact, pixels on a polar stereographic map at about 20 degrees latitude are about half the physical area on the Earth as pixels at 60 degrees latitude. And you can see that in the table. So for that reason, polar stereographic maps are typically used just for areas closer to the pole, say 60 degrees and greater, because in that latitude range from say 60 to 90, the projection is about 14% different in pixel area and preserves the local shapes of the map features. So now we know something about how two common map projections distort the physical areas of the Earth and how map projection pixels can be different physical sizes in square kilometers. Let's look at how map projections alter some calculations. So what I've done for this example is map sea surface temperature to two different map projections, a geographic map projection and a polar stereographic map projection. So I've masked out all the data south of 60 degrees, and I've also masked out ice. And I've calculated the actual mean sea surface temperature value of 5.10 Celsius. And I'll show you how I did that on one of my next slides. But for now, let's look at how the projections produce different results. Now, on the left is the polar stereographic map, and its pixels are roughly the same physical area, only about 14% change in the map. On the right is a geographic map projection with vastly different pixel sizes. So for example, from 60 degrees to 80 degrees in this geographic map projection, pixels are about 3 times smaller in area. So what we find is that we get different mean sea surface temperature values when we compute just the mean pixel value, disregarding any difference in pixel areas. The polar stereographic mean pixel value is actually fairly close to the actual value, just about 2% off. The geographic mean pixel value is much lower. And so the question is, why is that? Well, you can see that the data distributions are very different when comparing geographic versus polar stereographic, even for the same data. So what do we see here? Take a look at the red line, the geographic map. As the sea surface temperature pixel values get warmer, the normalized count of pixels decreases even though it tracks the same set of peaks and valleys in the histogram as the polar stereographic. Well, that makes sense because warmer pixels are further south, and as you go south in the geographic map projection, each pixel takes up a larger area, so at southern latitudes there are less pixels per physical area on the Earth. And what that means is that pixel count data is artificially skewed to be higher towards the poles because a lot of smaller, colder pixels at higher latitudes have been used in computing the mean pixel value in the geographic map. So that lowers the mean pixel value compared to either the polar stereographic mean pixel value or the true mean sea surface temperature value. So let me show you next how I computed the actual mean sea surface temperature regardless of the map projection. The formula on the left and the code below it is just computing the mean value of the SST pixels. It doesn't take account of any physical square area difference between the pixels in the data, so the results vary depending on which map projection the data is in. The formula on the right weights the sea surface temperature values of each pixel by the physical square area of each pixel and then divides by the total area of the pixels. So in that way, pixels that are smaller in physical area are weighted less, and larger area pixels are weighted more, so that the mean value reflects the mean of the overall area being measured. When we run the area weighted formula on the right on either of the polar stereographic data or the geographic data, we get the same result, that 5.10 mean sea surface temperature value. So now I'd like to also talk about another method of getting the same result, which sidesteps the issue of different pixel areas. Another solution is to use data that is on an equal area projection. That's a projection that distorts the shapes of areas of the Earth, but each pixel represents the same physical square area. So you can see a good example of that distortion in the sinusoidal projection on the right. You can take data in any projection and reproject it to an equal area projection and then compute statistics on the data and get the same result as weighting each pixel like we showed on the previous slide. However, reprojecting your data isn't always practical. So now that we have some practice in thinking about pixel areas, We can also apply this knowledge to sea ice extent calculations. So the plot on the left shows ice classification data in the Arctic Ocean from the METOP-C satellite. And the ice is broken down into seasonal, mixed, or perennial ice. The data is distributed in a polar stereographic projection by the data provider. So suppose we wanted to show how much these classes vary over time. We could write code like the snippet shown at the bottom right to loop over each pixel in the data set and add up the pixel areas for each pixel belonging to a specific class. And what I did is I ran the code snippet over a time series of files for each class, and you can see the results in the graph on the right, which shows how the ice classes vary in a regular seasonal pattern from 2022 to 2024. So for this data, you could compute an estimate of each pixel area manually inside the main loop like I did, or you could have the pixel area pre-computed in a data file that you could use so you don't have to keep recomputing it for each run. So now I'd like to show a final type of data analysis that varies with the map projection. Take a look at the plot on the left, and suppose that we're considering the straight blue line through the ice thickness data on a polar stereographic map. Imagine that this is maybe a route that an ice-breaking ship would take, and we want to find out what ice thickness we'll encounter. The blue line represents a straight route in the polar stereographic coordinates, and the red line is a straight route from a geographic map projection. And you can see when it's overlaid on top of the polar stereographic map that the line from the geographic map becomes a curve. So in general, straight lines on map projections are not straight lines on the Earth, except for unique map projections like mnemonic projection, for example. On the right are the very different line surveys produced by these two lines. And notice that the geographic line survey indicates much thicker ice along the route, which would be the wrong route to take if we were using that to guide the ship. So what's the true answer, though? Well, the ideal would be to compute the geodesic between 2 points and then extract data along that route, the geodesic being the shortest path along the Earth's ellipsoid between 2 points, or a straight line on a mnemonic map. It turns out that neither the polar stereographic survey line or the geographic map projection survey line are actually correct, but the polar stereographic line is much closer to the geodesic. I'm going to stop there because I could go on and on about data analysis on map projected data. When I did this talk live, there were a few questions, but if you have some after watching this video, put them in the comments and I'll do my best to answer them or send you to somebody who can. I've given some of the links here to the course page, to the data that I used, and to the code snippets that I showed on my slides, as well as other code snippets I used to create some of the figures. You can use these code snippets as input to the cwscript command, which is part of the CoastWatch Utilities software. And thanks everyone for your attention. I hope this has been a useful video for you.